In this video, I'm going to go over how to take high-level FMCW radar concepts like generating frequency-modulated signals and subtracting signals frequencies, and show you how they're actually implemented in hardware and software. This is actually a series on FMCW Radar, so if you're shaky on the basics, you can just pause this and check out the first video, links in the description. I'm also really excited for the next few videos, so subscribe if you want to see those. But here we go with this one. Let's first go over a simplified block diagram of an FMCW system to show its main components. As you might expect, the diagram is mostly split into two sections, one for transmit and one for receive. You'll see slight variations depending on the designer or the use case, but the main blocks will stay roughly the same. In this diagram, we have some blocks that are actually a collection of components, like this signal generator here. We also have some that condition the signal by amplifying it, filtering it, or splitting the power in two, and one that multiplies our transmit and receive signals together. We then also have a block that sends our signal into the digital domain for further processing. And of course, we have the antennas. Let's first dive into the collection of the components represented by this signal generator block here, and in this case we'll talk about one implementation called a phase-locked loop. This is what allows us to create those frequency-modulated signals I mentioned in the last video, like a sawtooth or a triangular modulated signal. A PLL explanation could easily span multiple videos, so in the interest of not making this an hour long, I'll give an overview, but I highly recommend looking into it further, so I included a good article about them in the description. The PLL is made up of a few more components, starting with a phase frequency detector, or PFD, which feeds into the loop filter, and then a voltage-controlled oscillator, or VCO. Part of the VCO's output is then sent back into the PFD, where it's compared with the original input signal, but first it goes through a block that multiplies the frequency by a fraction. That's quite a bit, but let's go through it, block by block. For a second, we can just ignore that feedback input to the PFD and focus on this input. It expects a reference wave with which to compare the feedback, so we can hook it up to some form of local oscillator like a crystal to get a clean reference tone. Let's say this is 1 MHz. The PFD's job is to produce a current that we'll call I, which is proportional to the frequency difference of the two inputs. Meaning, if the LO input is higher in frequency than the feedback's input, the output will have a positive current, and a negative current when the LO is lower in frequency than the feedback. How it does this is super cool, so I'd love to make a whole nother video just on that, but I'll finish this one first. In this case, the feedback doesn't have a signal yet, so the output will be a positive current. This proportional output current will have some noise, so it gets low-pass filtered by the loop filter to send a clean signal to the voltage-controlled oscillator. This filtering is vital to the operation of the PLL and determines some key characteristics of it, but that's kind of getting into the weeds, so in this video we'll gloss over it. The VCO itself is a really cool block because it takes this filtered input and converts it into a signal with a frequency proportional to the input voltage. So depending on the negative or positive inputs from the PFD, the VCO will decrement or increment the output frequency. So we have an output signal, but without some sort of feedback loop, the output of the PFD would just remain positive and the output frequency would continue to rise indefinitely. So to set the output to a stable frequency, we finally connect the output to the other PFD input through that 1/n frequency divider, which for now let's say has n equals 2. Assuming n equals 2, the divider's output will just look like the VCO output with its frequency halved. The PFD will then compare these two signals and see that the LO input has a higher frequency than the feedback, which means the output must be increased. So it sends along a high current, which causes the VCO to increase its output frequency. This process repeats, looping over and over again, slowly increasing the frequency until the output frequency equals n times the input. Once it reaches that desired output, the output is locked. While locked, it sends alternating positive and negative currents, which helps to reduce the chance of the output frequency drifting over time. This is still just a constant output frequency though, without any ramping. So where does the frequency modulated in FMCW come from? To configure this frequency now, our n divider normally comes with some sort of programming interface so we can change its n value. By changing this end divider value, we can then modify our output signal's frequency, and we could even change this end divider in small increments over time to achieve an output with a frequency that looks like a sawtooth or a triangular wave. In reality, these steps would be much smaller to closer resemble the sawtooth signal or whatever other modulation type you're using. And there's our FM signal. Okay, so the first block is done. Let's pull back from that signal generator block and head back to our main block diagram. Once our frequency modulated signal is generated, we send it to the next stage to be amplified. Then split into sections for transmit and receive, often using a splitter which splits the power in two, or we could use a coupler which wirelessly couples a smaller amount of the power from our main transmit path to the receive path. And then the transmit waveform goes to the antenna to radiate into the world. So moving into the receive path, we now have our reference transmit signal, and after a short amount of time, we'll have our receive path which has reflected off the target. This isn't quite the beat frequency yet, and remember we need that to compute the target range. We still have to compute the beat frequency by finding the difference between these two signals' frequencies, and that is done using this block right here. This is seriously one of the coolest RF blocks in my opinion, because it's a direct hardware implementation of a basic math operator, which, as you can probably guess from the symbol, is multiplication. And this is how we achieve the frequency subtraction to get the beat frequency of our target. So we multiply to subtract? Yes, and this is more clear if we look at our two signals for what they are, sinusoids, which is just a collection of sine waves. First off, we have our transmit signal operating at ftx, which itself is a function of time. Let's say at t0, this is 12 gigahertz. This goes into the local oscillator or LO input of the mixer. The LO is normally the most powerful input, and so it's used to power the internal switching circuitry, but the implementation of this device is probably out of the scope of this video, so I'll link a great talk about them in the description. After the signal reflects off the target and returns to the receive antenna, we have another signal, still at ftx, but it was generated from some time ago, say t-shift. Let's just say that frequency is 10 gigahertz, and this goes into the RF input of the mixer. As a quick refresher, these two signals would look like this if plotted together, where the receive signal is equal to the transmit signal, but shifted in time. So at any given point in time, we have two different frequencies. In a real system, this 2 gigahertz difference is pretty unrealistic, but something this big is just better for visualization. The mixer takes these two signals, and using some balance and switching diodes, out comes the product of the LO and RF inputs from the intermediate frequency, or IF port. This signal is unlike anything we've seen before, and it definitely doesn't just look like the transmit and receive signals with their frequencies subtracted, so let's dive into that. Now I failed trigonometry in high school, but hopefully you tried harder than me and remember that when we multiply two sine functions together at different frequencies, we actually get two sinusoidal outputs, one with the frequencies summed and one subtracted. So if we say f1 is ftx and f2 is frx, we can then plug those straight back into this trig identity and see how this signal decomposes into two different sinusoids. This comes out to be one signal at 2 GHz and one at 22 GHz. And you may notice that one of these is a sine wave at the transmit frequency minus the receive frequency, or in other words, the beat frequency, the very thing that we're using to compute the range of our target. There is still this high frequency term that we don't want, but it's pretty trivial to just add a low pass filter here to remove it since it's so far out of the desired band. After that low pass filter, we should just have a signal at the beat frequency like we want. Unfortunately, there are still some problems with this. Let's plot the signals to make the issue a little more obvious. Here, the x-axis is frequency and y is the power at those frequencies. One issue is that there's really two frequencies at the RF port that will output the same IF frequency. Since one of the products we get is the difference of the LO and RF ports, any two RF frequencies with the same gap from the LO will output the same IF tone. This means if the target we care about occurs at 10 GHz, but there's some additional noise at 14 GHz, because there's always going to be noise at all frequencies, the power seen at the IF will be artificially inflated by the noise, which would make us think that there's actually a stronger target corresponding to that received 10 GHz frequency. And unfortunately, if we don't deal with this until the RF frequencies have been combined into the IF with the LO, they're basically inseparable because they've been combined into one frequency. We can deal with this though. To pull this undesired frequency out, we could do some filtering before the mixer, because here the RF signals are summed but still separable in frequency. So let's add that filter. This could just look like a bandpass filter around our desired band, which is below the 12 GHz LO frequency, or we could use a low-pass filter with a cutoff near that LO frequency. Here's an example of one that's used in Analog Devices' phaser radar system that I've worked with. Link for this will be in the description. Once applied, the output isn't perfect. We still have some of the undesired signal above the LO, which will make it into the mixer and contribute to the IF or beat frequency, but it does clean up the signal pretty well. But luckily, mixer designers have also noticed this flaw, so there is also the option of choosing a single sideband or SSB mixer. This basically accomplishes the same thing, where it only allows the band above or below the LO frequency to pass to the IF port. If you get the high side variant, the band where the LO frequency is greater than the RF is allowed, whereas the low side variant allows the band with the LO less than the RF. So in our case, we would choose the high side since the LO is 12 GHz and our RF frequency is 10 GHz. Up to this point, we've taken a reference sine wave and generated a frequency modulated signal from it, conditioned it a little, transmitted it, and then once it returned, we mixed the two signals together to get the beat frequency. That's cool, but how do we get from this, just a collection of beat frequencies from various targets, to something actually intelligible by humans? We need to get this information into a computer-readable format so that we can start processing it. And computer can mean a lot of different things, but they all have one thing in common. They need this analog signal in the digital domain. So let's send this signal through an analog to digital converter and enter the digital domain. Until now, we've talked about this beat signal in the time and frequency domains pretty interchangeably, but what's really flowing through these transmission lines is this time series signal. So when we send it through the analog to digital converter to later process on a computer, the sine wave at the beat frequency gets broken into a series of uniformly spaced voltage readings, where the spacing between these readings is 1 over the sampling frequency of our ADC, or the sampling period, and we'll use this in a second. So if we call our input signal x as a function of time, then we'll call the digitized signal x of n, where n is the index of the sample instead of a continuous time. But since with just the samples showing, it's kind of hard to read, I'll add back the line between the samples for visualization. So now that the beat signal is in a computer-friendly format, we can start doing the real fun stuff. A quick disclaimer though before I get into the signal processing. In this video, I'm only going to cover the range calculation portion, but there are so many cool things that can be done here. I'll link a few of my favorite applications in the description and make videos of some, but there's just way too much to cover here. There are also some parts you'll see in the next section that I'll gloss over in the interest of getting you enough information to start out without having an incredibly long video. But I'm also already planning to cover some of them. If you remember from the last video, we found this equation for the range of a target given its beat frequency. But in a real-world scenario, the signal seen at our receiver isn't just the beat frequency, but actually a time series signal that contains the reflected signal from the target at its beat frequency. It could also contain multiple targets within our viewing range, each with their own beat frequency. And I'll exaggerate the difference in frequency for visualization, but really these would actually be pretty close together. There's also some noise from various sources because the environment we're scanning isn't perfect, and there may even be reflections from unwanted targets, like the ground or a wall. And those will have their own beat frequencies too. This is called clutter, and it can be pretty hard to deal with. So it actually looks like a pretty messy signal when you consider some of the sources other than the desired target in an environment. But we can partially differentiate between them to find our clean beat signal if we look at the signal's frequency spectrum. Each of these peaks will correspond to a target, whether it's desired or not. And again, these are just samples, but it's easier to see with continuous signals. But how do we get from these time series samples to the actual frequency spectrum? Well, if we just did the Fourier transform on x of n, we'd get a sampled frequency spectrum as the output, which we'll call x of k. Luckily, pretty much regardless of what language you're using to implement this, there's probably already an implementation of the fast Fourier transform, or FFT, available to you, and there's tons of great videos covering it. For simplicity's sake, I'll show you the code in Python, but the concepts will transfer well to other languages and platforms. If we go back to our sampled signal and its discrete Fourier transform, we can start looking at the code to go from one to the other. And let's get rid of the x of k spectrum so we can see the output at each step. We can start by defining some things about our sampled signal, like for how long we're sampling, in this case 4 seconds, and the rate that we're sampling at, in this case 1,000 samples per second. Neither of these are necessarily realistic, but they are good for visualization. Then taking those, we can find the total number of points in our signal, which will give us 4,000 of these sample lines. For the next few things, we'll need to import some packages, but don't worry about this. I'll include all this code in the description. Next up is we can multiply our samples by a window function, which just helps us clean up the frequency spectrum and make it easier to differentiate between the frequency peaks. And that could be a whole video by itself, but we'll kind of skip over it to get to the really interesting part. Now we get to compute the FFT over some number of points we define, and I'll just leave it at the same length as x of n, or just n. There are multiple other things going on here, like dividing the transform signal by half the number of points in the signal, which normalizes it, taking the absolute value because the log function isn't defined for negative inputs, taking the logarithm of the FFT to make it more readable, and computing the values for the frequency axis. But the important part is we now have our signal x of n in the frequency domain, but now the frequency spectrum is also sampled, so we'll call it x of k, where k is the index along the discrete frequency axis. If you're familiar with sampling, you'll know that this axis actually extends from negative pi to pi, or negative half the sampling frequency to half the sampling frequency. But for this, we won't look at the whole x-axis. We really just care about the positive frequencies, and many times just a subset of those positive frequencies. But remember, the range of the targets we're trying to find is a function of these beat frequencies. This means that we could just take these x-axis values and plug them straight back into the range equation to get this received power spectrum, not as a function of frequency, but range. So we now know that peaks 1, 2, and 3 correspond to ranges 1, 2, and 3. This is super cool, and it even gets its own name, the range FFT spectrum. What's even cooler is that if you look at the left of this range FFT spectrum, you'll notice that we have data all the way down to 0 meters from the antenna. This may seem obvious, but it's actually a huge benefit FMCW radars have over their pulsed counterparts. Like we talked about in the last video, a pulse radar transmits a signal and then turns off the transmitter and waits for a return. This means there's this whole pulse width that we'll denote tau, where the receiver is just completely off. So looking at the receive side, it's only really on during these pulses, or really even smaller because there's some setup time in between. If we were to get any reflections from targets in that transmitting time, it would be impossible to know. But this transmit pulse width is on the order of like a microsecond, so does it really matter? Well, if you take into account that this transmit wave is traveling at the speed of light, that microsecond becomes 300 meters of travel distance, or really half that because the wave travels there and back. This is called the minimum range or blind range, and it'll scale depending on that pulse width. Since many FMCW radars are constantly transmitting and receiving, they don't have this blind range problem, which is really awesome for applications like automotive radar, where you really need to be able to see other cars and obstacles, especially when they're very close to you. Now, hopefully you have a slightly better understanding of what some of these components in an FMCW radar block diagram do, but we're not done yet. This range FFT spectrum we calculated is just the tip of the iceberg, and I'm super excited for the next video. In that video, we'll take this concept of having our x-axis as range bends, and then we'll take a bunch of sets of samples like that and expand it into 2 and then 3 dimensions, which will tell us about the target's range and velocity over time, which is seriously one of the coolest FMCW concepts in my opinion. Thank you all so much for watching. As always, resources, caveats, and all the source code for this video are in the description. I really hope you enjoyed, and stick around for the next one.